right, welcome back. So, in the previous video, we had a look at basically clearing a screen with a color, and that's fine. We can do that. It's nice. What I'm going to do over the next two videos is make a triangle. Now, I know what you're saying. Make a triangle in RGB? That's never been done before, but we're going to do it. There are two major components to this. Hence why we're going to do it over two videos. Ugh. There are two major components to this, and in order to really get into it, I'm going to just talk briefly about the philosophy of modern OpenGL. So we have our computer, and our computer has our CPU, and the CPU has everything that we can access. So our disk, our RAM, all of that stuff. And then it has the GPU, and even though the GPU is attached to the computer, is attached to the CPU, there is sort of a communication protocol between them. So there's a number of little contact points between these things. And modern GPUs work better when you ship as much stuff as possible up front, let it do its thing, and just send it little messages. And that also goes for the code which runs on the GPU. So the two tasks that we're going to do is, first of all, we're going to write some shader code and send that over to the GPU, and the GPU will take that code and compile it, and that's the program that it will run. That's this week, and then next week, or in the next video, we are going to send data over to the GPU so that the GPU knows what to draw. So this will be like how to draw, this will be what to draw. Now I've cheated a little bit, so for this video, I've actually done the data part up front. When we get the shader code done, we get our shader up there, we're going to see something straight away. And then next week, we're going to have a look at how to actually send data. But that is the approach that we're going to take today. So just a little bit about shaders. And my favorite way to explain this is to look at the graphics pipeline. And I'm going to ask you a question. How can we draw this triangle? Okay. So first of all, we get some points. We get some input. There we go. There's 3 points. And we need some sort of, this isn't anything that we control, but it happens under the hood. There's some sort of input assembly. In other words, the graphics card looks at the data and says, the first 3 points that I get, they make a triangle. The next 3 points that I get, they make another triangle, and so on. And then we get to a vertex stage. And a vertex stage is where we take these points, and we're not going to apply any transformations here, but just as an example, we might want to apply a transformation. So, okay, so there's sort of a flow of data. So the data flows from left to right. We get the points in, we send those points to the vertex shader, and then the vertex shader sends points along to the fragment shader. When I say fragment shader, think pixel shader, okay? Actually, back in the early legacy OpenGL, these things were actually called pixel shaders. But anyway, fragment shader. And in between, by the way, in between there's something called a rasterizer. What the rasterizer does is it actually interpolates. So it goes along the edges, and then it goes between, fills in all the points, breaks it all down into a bunch of little jobs, and then the fragment shader, all it sees is a single pixel. And the question it is answering is, what color should that pixel be? So it does its math under the hood, and it says, this one, I return the color green, that pixel should be green. And then somehow, that is a pixel in the final image. Okay, so that's a really brief overview. Now I'm going to go a little more in depth. So assume that we have, for each point, we have 2 attributes we really care about. We care about the position and we care about the color. Okay, and each of these data points has a data type. So the position attribute will be a three-dimensional vector, x, y, z. I guess, why not? Yeah, so we'll call that, actually, you know what? Scratch that. Going to make it a two-dimensional vector because we're just viewing it on screen, right? I don't want to confuse it too much just yet. So we get x and y. This is a two-dimensional vector, and the standard OpenGL name for that is a vec2. Two components, floating point numbers, there it is. Okay, now for the color, we're going to have red, green, blue. That is a three-dimensional vector, vec3. That's it. All right, so this is getting a little messy. Okay, so where were we? And I promise we are going to get to the coding at some point, but let's just keep visualizing this flow of data. So we have our vertex stage, our vertex module, and into that, I like to label attributes according to their destination. So I'm going to call this vertex, this is just to save space, vertex position comes in. So that's coming in. And then we're also going to take vertex color. Okay. And I'm going to label these just to help. So I'm going to call this attribute 0. I'm going to call this attribute 1. Again, this is a vec2. This is a vec3. I guess if it helps. And then what we're going to do is we're going to have the fragment shader. And then, well, the vertex color will just go across, and I'll call that frag color. Again, that will be a vertex vec3, no modification. Now what's going to happen with the vert position, this is a little funky. It doesn't get passed directly to the fragment shader, but instead it gets specified. There's a global variable called GL position. And if we set the value of GL position inside the vertex shader, that will be set as the position where the thing appears on the screen, and the rasterizer will read that just fine. It's a sort of funky thing, but there it is. And then, whoops, a little funky. Then we'll just have some sort of, I'll just call this color. And this is a vec4 because it'll be RGBA, and that'll get written to the screen. Okay, so that is the design that we're going to go with for this program. But there's a little bit more to it because we also need to write code. First of all, we need to write the shader code, but then we need to write code which will read the shader code. Okay, but you know what? I think the best way to do that is just to get into it. So let's get into it. Alrighty, so here we are in our environment, have things open. Now you may find when you go to build this, sometimes if you're pasting a folder over from one to another, it gets this error and it says, what does it say? This stuff doesn't match the source used to make a cache. Okay, so this is weird. If we look in build, there's this cmake cache.txt. Basically, you need to delete that and rerun it. But what you can also do is if you go view command palette and just go cmake, here we go, this delete cache and reconfigure will probably do the same thing. There we go. That's built. We'll just go ahead and run it. Oh, there we go. Okay, excellent. Great, I'm happy with that. So we'll just go to the source folder and just make a new folder, and I will call this shaders, and this is where I'm going to write my shader source code. So then we'll just go new file, and we'll have two of these. We'll have vertex.txt and fragment.txt. Now you don't have to use .text. You can use I've seen .c as well, or .h, and it actually gives you some IntelliSense, but I like .text. It's just my thing. So what I'm going to do is I'm going to write just a basic sketch. So I have inputs, we'll have vertex position, and that will be, I'll say vec2. Yeah, vertex color. Okay, the outputs are fragment color, which would be a vec3, and then there's some stuff like the program's going to run. What I'll do is I'll just save that, and I'll just copy all of that, make a new file. Okay, so now the inputs of the fragment shader are basically that fragment color. And the outputs, well, there aren't really any outputs except for the color that we set on the screen. But I've talked around things enough, so let's actually get into the job of doing it. So, whoops. All right, so first thing I'm doing is I'm just specifying that I'm going to run this in OpenGL version 3.3, and we're running in core profile, which is modern OpenGL. The opposite of that is, I believe, immediate profile, which is legacy OpenGL, but that's old tech, okay? If anyone comes up to you in a dark alley and starts talking about GL begin and GL end, just start running the other way, because it's not good. It's a nightmare to debug. You have no idea what's... I don't like it. I do not like it one bit. Okay, so what I do like is being extra explicit. So I'm specifying that I'm going to take in a vec2. Yeah, going to take in a vec2. I'm going to call that attribute 0. I'm specifying that here. And I'll do the same thing. Oh, geez, this mouse, this trackpad. Okay, so layout. There we go. So we're taking this, it's attribute 1, we're taking it in. It's a 3 vec, and it's called vertex color. Okay, great. And now I'm going to do the same thing with my output, but with this output, because I have control within the shader code, I'm just going to list it by variable name. So I'll go out vec3 fragment color. And there we have it. So then we just go, all right, didn't declare the main function. And like I was saying, this is a little bit of a funky thing, but this GL position is a global variable. If we set it, it will set the position on the screen. I think in the provided code, I'm actually taking vertex pos as a vec3, so this may differ a little bit from the provided solution, but you should be able to see what's going on. If we're making a 4D vector and the last component has to be 1, then we just pad in with the rest. Now, fragment color is going to be the vertex color with no change applied. So this vertex shader is really doing nothing. It's just passing the data along. This stuff gets passed to the screen. It needs to be a vec4. The last component needs to be a 1. There are reasons for that. I'm not going to talk about them right now, but they are very important. I just don't want to overload it. I'll talk about that next in the next video. Right, so yeah, and then we pass this along. All right, so let's go to the fragment shader, and I think this really helps if I see these right next to each other. Okay. All right, cool. So hopefully you can see the data flow here. We get this attribute in, we work with it, and what we want to do is we want to output a vec4, red, green, blue, alpha, screen color. Okay, so I like to always label variables according to what their destination is, because, you know, otherwise they'll all be named the same thing. It's all color, right? So I will declare the main function. And again, all I'm going to do is take that color that I've got right now and give it an alpha component of 1. Excellent. Cool. And then you might be saying, well, wait a second. If we're just giving 3 corners, but we're not transforming the color, how is the color ever going to get blended? Well, Remember, the rasterizer interpolates all attributes, position, color, anything that you throw in there. But we'll see more of that later. Okay, what I want to do right now is I want to check that we can even load this stuff. So to do that, I've actually got this, I've made this config file here in the previous video. I'll stick with that, I'm happy with that. I will just add the following. There we go, cool. So this is just so we can basically, open files, stream files into strings, and know about strings. That's probably a good thing to know as well. So I'm going to go back to my main file, and we'll have to sort of break this up a little bit, but first of all, I'm just going to check that the thing even works. Okay, so what I'm doing is just the simplest operation of opening up a file and printing all the lines of the file out to the console, just to check that I've got my file paths right. So I'll just give this a go. There we go, and as you can see, it has not loaded the file correctly. So this is the point where there may be a little bit of experimentation. In macOS and Windows, macOS and Ubuntu, I found it was sufficient to do this, to go, whoops, why did it do that? Yeah, to go back by one level, because, if I've got this right, it's sort of running from this environment here. So we go back by one folder, then we go into source, shaders, and let's see if that works. Yeah. As we can see in the console, it has printed out all the contents of the file. So that is the correct way to get the file path. Now, what I did on Windows is I just found that it just wasn't working. And I found that I could fix it by grabbing that shaders folder and just pasting it into the root folder where the executable was, and just getting rid of all this stuff and just going shaders vertex.txt. Point is, it's a great idea just to get this working and check that it is loading the file first before going through and making all the stuff. But I'm happy with that. So what I'm going to do is just pretty much just get into it. So I'm going to, I'll just go right down the bottom, give myself some space, and I will make a folder function that basically takes a file path and makes what's called a shader module. So we'll have a shader program, that's the whole thing, and then shader modules are the individual parts of the program, like the vertex shader, fragment shader, stuff like that. Okay, so what I've done here is I'm going to open the given file path, look through it line by line, and then instead of dumping that onto the console, I'm going to dump it into this string stream. It takes a whole bunch of strings and builds up like a mega string, which holds all of the source code in one go. Right, so now what I'm going to do is I'm going to just do a few things. One thing is I need to actually convert this from a C++ like standard library string into a C style character pointer string. And I'll do this with a very imaginative renaming. The way I'll do that is go shader source and use the C-string method. Okay, and there are reasons for this, but anyway, then the next thing I'll do is I'll just basically erase. It doesn't matter, but this is just an example of erasing a string stream. Not that we actually need to, because this will automatically be closed. Actually, the same thing with this file because of RAII, but we don't necessarily have to rely on that. Okay, so we've loaded the file. We've collected all the contents of the file into a single string. The next thing I'm going to do is basically compile the shader module. Okay, so just had a look there. By the way, please get comfortable reading documentation. It's super important. Super important. But what we've got here, just minimize that for now. Okay, so we've created the module, and all objects in OpenGL, or most all objects, are referred to as unsigned integers, which we can think of as just some internal memory location. Like this is thing number one, thing number two. And it's a little more complicated than that, but that's how we can understand it. What we do, first of all, is we create the shader module. There we've got it. And then we attach some source code to the shader module. And we can actually attach multiple source codes. And this last argument here, this is the thing that I was looking up, is the length of the source code. But if we specify null, then it'll, I believe, just look through the whole file. Next thing we need to do is actually compile that. So we'll go compile that. And that's fine. But as we do more of this, they'll sometimes fail. So we want to check whether that compilation was actually successful. So we'll get the shader integer value. And what we want to do is we want to read the value into the status variable. And in order to do that, we'll pass in a pointer to the status variable, which is done with the address of operator. There we go. Okay, so there are ways that we can actually query how large the error log is, but I've found in practice that 1024 characters is usually enough. So we just allocate 1024 characters, read off the error message, and then just dump that out to the terminal. So if we get to that point, then yeah, all good. Just return the shader module. Remember, shader module is referred to by this unsigned integer. There it is. Right, so the next thing is that'll make an individual module. So that'll make a fragment shader, vertex shader, and so on. But then we want to make an actual program. Okay, so going to have to pop back to config for a second because, well, we'll need two modules. We could allocate an array of modules, but let's use some standard library stuff. I thought so, we haven't got it yet. I like vector. And vector pretty much is a resizable, basically it's a resizable array, I'll say that. There we go. I mean, pretty much it is what you'd expect. So we pass it in, we say, hey, I want to make these different modules. We collect those together, and then we're going to use it all. So just the same as with the module, we will basically create a shader program, then attach the modules, and then link it because those modules have already been compiled. All right, cool. So as you can see, that pretty much is what I said. We create the shader, attach the modules one by one, then link it all together. Now, of course, we may have an error, and we can actually check that pretty much the same way that we did before. Oh, that's a good spot. I just realized that should be success, not status. All right, cool. So we've got any error messages if we need them. Now another thing, which we didn't do with the other one, but those modules are independent of the shader program. They're just little chunks of code. We compile them, we grab copies of them, link them together and stuff, but then we don't need them anymore. So we can just go ahead and delete all of them after linking. And then finally, we can return the shader. Okay, great. So how does this stuff get used? Well, set the clear color. After setting the clear color, let's create that shader. There we have it. And I might as well just get rid of that other code because I'm happy that that's working. Okay, so we've got the shader, that's fine. Then what I'll do just before ending everything is I'll delete it. And additionally, when I'm in the program, part of my, drawing the frame and everything, I will use the program. I know what you're thinking. Hey, we very clearly do not need to just call this every frame. I mean, we've only got one shader program, but I think it's good habit to get into because when we move on and we get more shaders, we'll have to coordinate that. But yeah, so if we were to run this right now, hopefully we don't get any errors. We probably won't see anything either. Ooh, okay. What do we have here? I think I messed something up. What is that, line 86? Oh yeah, this as well. Okay, I think that's fine. Just normal typos. Okay. Right. Okay, so why did I not think of this? That's fine. So see that make shader is calling make module, but it's saying, hey, by the way, I don't understand what that thing is. Now I go back and forth on this, but I think it is good to declare things from top to bottom. So we can see that main is calling make shader, and make shader is calling make module. But the downside to this is when we get to main, it hasn't seen make shader yet. So we'll have to just declare these up the top and define them down below. It's standard practice in C++. There we go, we've got the prototypes up above. Now let's give that a shot. Yep, there we go. Okay, cool. Right, so we've got the shader program. It's there, We got no triangle. Well, of course we got no triangle. We haven't sent data to the GPU yet, but let me just give me 1 second, I'll whip this up. So I'm just going to grab this. If you look in the worked solution, it's there as well. Just pretend, I'm cheating a little bit, just pretend that we have some triangle that has been made for us. There we go, we've got this triangle mesh. So we'll go ahead and include that. And we will also need to go down to the CMake lists and declare those files. There we go, cool, we've got that. And now we'll have to actually use that. So again, just pretend this is all good. Okay, so we've made that triangle mesh, and then down below, we set up that we're going to use our shader program, and then we draw the triangle. And under the hood, what that triangle mesh is sending a bunch of data to the GPU, so it has it. We'll look at that next time. But, okay. Oh, whoops. That should be .h. As I say every week, it's OpenGL for the beginners, but I am the beginner. But hey, even this beginner managed to get a triangle on the screen. How cool is that? Alright, so I hope you can appreciate that a lot of stuff goes into getting that first triangle on the screen. Today, we just focused on the source code that runs on the GPU. So just imagine this program is running on the GPU in the background. And next week, we're going to deal with shipping the data over to the GPU. That's the stuff that I flashed through today. Shipping the data over to the GPU so that it can be drawn. I hope you can appreciate the excitement of climbing OpenGL Mountain, and I hope to see you again next time. But yeah, happy coding, all the best, and I'll see you around. Bye.